Okay, thanks. Someone help me press record, is it? Oh, okay, thanks. Now only I saw. Okay. Okay, yeah, thanks. Well, since I have time, I can repeat myself a little bit. So, yeah, this is for the recording. So I'm going to calculate the moment of inertia of a two-dimensional object. And, well, what I wanted to do is to calculate this. Firstly is to find the expression for dm. And I convert it into like this, right? And then this dm is one piece over here. So the mass per area is sigma, and it's a constant. So the dA over here is the area element, and the area element is the width times the height. So the dA is a dy. So we substitute this in. Right, so so then the rest of it is just math. So I'm gonna scan this and upload to the Moodle. If we consider 3D and the constant will just be density, yes. So I'm using the word density to depend on the dimension of the object. So for 2D object, the density is the area density, so the mass per area. If it's a 3D object, density is mass per volume. Yeah, so okay, yeah, so okay, then what else? So I got the m in terms of y already. Now this is the trick, right? This is how we avoid doing multiple integrals. It goes like this. So remember, so the trick is the following, is to think of the door as a stack of many rods. Okay, so is there a message? So the door is a stack of many rods, and that means we are going to use this fact. Okay, so a door is the sum of many rods. Okay, so let's look at one rod. So this is having a one rod, and this one rod will have the moment of inertia di rod, right? So so over how to write? So let's say one rod of mass, it is an infinitesimal mass dm. So it has mass dm. So therefore the moment of inertia is the I rod. Okay, because the mass, the moment inertia depends on mass. So if the mass is small, then I rod will be small. Yes, yeah, that's the answer. dA is the area times the height. Okay, so yeah, it's area length times, so the area of this thing. So now the formula for the rod is this formula. Now if the mass is small, then the moment of inertia, the whole thing will also be small. So that's why I write di rod, right? So di rod is 1/3, and then the mass, and then the length, which is a squared. Okay, so yeah, so we got this now. Yes, correct. It's the same idea as calculus. Okay, so so yeah, so this is one rod. So the full door will be the sum of all the rods, right? So that means it will be the integration of all the rods. Do you follow so far? This, I'm avoiding using the original formula. I'm just saying that I already know the moment of inertia of one rod. Okay, so this is the moment of inertia of one rod, but the door is the sum of many infinitesimal rods. So I just stack up all the rods and add up all the results. Okay, everyone follow so far? Okay, so so that means I just need to integrate this. That means I just I rod is given by this expression. So I 1/3 is dm, and then a squared. So the dm expression we have already found, which is over here. Okay, so put it here. Then what we have is the integral of 1/3 and then m over b dy, and then there's a square at the back, don't forget. So just rearrange everything to make it look nicer. The constants, I can take it out. Okay, so all these are constants, so I got ma square over 3b, and then I'm just integrating y, just integrating nothing but dy. And then again I got a y integral, so the y integral, just put in the limits. The first rod is at 0, the last rod is at b, so same as just now. So the first rod is at 0, the last rod is at b. Put in the integration, and then yeah, so work out the rest. So this one will just give you b, right? So I got ma square over 3b times another b, so it will cancel, which is to say that I is just 1 over 3 ma square. So this is the moment of inertia of a hinged door. So it doesn't, it seems to be independent of b, right? It just depends on the total mass of the whole thing. So it's 1/3 ma square. Okay, so any question? Huh? Why is what amazing? You mean yeah, as in is we managed to avoid using multiple integrals, right? Yeah, so that is why. Okay, any other question? So this is the tricky part that I'm going to slow down and see if anyone got any question. So time to practice more calculus. Yes, definitely. So yeah, calculus is is independent of b. Yeah, it only depends on the mass of the thing, and then the a. Okay, so whether it's a long door or short door, moment of inertia is the same. But maybe the long door, right, if you use the same material, a very tall door with the same material, you need to use more mass, right? You need more materials, so the total mass will be higher. So it's kind of indirectly depending on the b. No need to memorize, no. So the I rod is the inertia for one rod. Yes, Charles, yes. Yeah. That's how we avoided because I already know the moment of inertia of one rod, right? Is this formula. But the door is nothing but a stack of many rods. So I just add up many rods, and then I just use the moment of inertia of one rod. Okay. Okay, any other question? So that is the way, right? Yeah, this is the way. Mandalorian. That is the way to calculate the moment of inertia. And yeah, you just need to practice calculus a little bit, then you can find the moment of inertia of almost any shape already. Okay, the basic idea is to identify how to cut the piece, and then you add up all the pieces. Okay. So the next two-dimensional object I want to show you is a disk. Okay, so again, let's consider a uniform disk. So moment of inertia of a uniform disk. Okay, uniform disk. So let's try to draw a disk. So a disk is like this. Yeah, it's very hard to draw disk. Okay, so a disk is something like this. Yeah, something like this. And then let us consider the axis passing through the center. Okay, so if it rotates, it's probably like spinning around the center, right? Like a CD player, DVD, Blu-ray, that kind of thing. Okay, so how do we find the moment of inertia? Well, for the case of the disk, right, it is a two-dimensional object. How do we avoid using multiple integral? So it is we treat this as a sum of many rings. Okay, so it's a sum of many rings. Yes, yeah, correct. So you guessed it right. We are talking about rings. Oh, you can find a Mendelian gift from here. That's interesting. Okay, so a ring will be like this, right? So let's draw a ring, because we have found the moment of inertia of one ring last time already. Okay, so let's say the ring, for this ring is currently of the radius r. The full radius will be, let's call this capital R. Okay, so the small r could be anywhere between 0 to big R, and the thickness of this is very, it's almost like a ring, right? So the thickness is very small, so it will be having some small thickness dr, and then the mass of this ring is another infinitesimal mass dm, right? So we have we start with the moment of inertia of one ring of radius r, one ring mass m ring, and then radius r. And we have found the moment of inertia to be, what was it? It's mr squared, right? Just mr squared. Mr squared. Yeah. Okay, wait. Just check. I suddenly can't remember. So mr squared. Okay. So yes, so we are on track. So it's for one, this is for one ring. Okay, so for one ring, this is mr squared. And let us try to express, so this is for the ring. Okay, so now let's talk about the disk itself. So this is a disk, that means uniform disk, which is to say that the mass per area is sigma, and if it is uniform, it just means that sigma is a constant. Okay, and again, maybe you can guess the answer already. Sigma is just the total mass over the total area, which is big M over pi r squared. But since we want to practice calculus, right, let me just show the calculation clearly, step by step. So basically repeating what we did last time, the dm, bringing the dA over, so I got this, right? And then what is the area of this thing? Okay, so if we were using multivariable calculus, right, the area will be two variable dx dy, but we want to avoid this. Okay, since we are thinking of this as a combination of many rings, so let's treat this as one infinitesimal area. What is the area of this ring over here? It's very thin, right? The thickness is dr. Okay, so the area of this very thin ring should be, well, imagine if I take the ring, right, and then I unroll the ring, I've got something of the length of 2 pi r, right, and then the thickness will be dr. So therefore we say that the area is, do you agree that the area is the circumference times the thickness of this ring? Okay, do you agree? Right, so basically what I'm doing is I unroll the ring, so I get something very thin, right, and the height of this is dr. I unroll already, the thickness is dr, and the circumference is 2 pi r. Right, so what's the area of this thing after you unroll it? Right, so it's 2 pi r dr. Dr is tiny thickness, yes, dr. So yeah, in calculus, so actually more in physics and math seldom use this notation. Dr means something tiny, dx, dr, or whatever. Okay, so tiny thickness. So now we have this now. So I will put this in. Okay, so what we have here is dm is equal to sigma 2 pi r dr. Okay, so that is my formula for dm. So what is the total mass, right? Total mass is the big M, and big M is obtained by integrating over all the rings, and that means I'm integrating sigma 2 pi r dr. So I can take out the constants, so I got 2 pi sigma because it's a uniform ring, sigma is a constant, so it's r dr, right? Then so now my variable is r, so now I can say who is my starting point and my ending point. My first ring, I start out with the smallest ring, right? And then I add up all the rings, so adding up all the rings until the outermost ring will have the total radius r. So I'm integrating from 0 to big R. Okay, so after we integrate, I got 2 pi sigma, and then I got half r square from 0 to r. So these two will cancel, and if I plug in upper limit minus the lower limit, which is 0, I got pi sigma r square. In other words, my sigma is equals to m over pi r square, right? So that is what we expected. The sigma, the constant dm dr, is just the total mass over the total area. Okay, so now I got my formula for sigma already. So my dm is my dm formula now I can put in this way. So it's m over pi r square, and then times 2 pi r dr. So actually I cancel this factor over here, and then I got my dm now. So it's just 2m over r square r dr. Okay. Okay, so do you agree so far? Do you follow? dm, right? So we got my dm until here already. So let us try to find what is the moment of inertia now, since we got the formula for dm. Okay, so as we were saying, right, the moment of inertia of one ring, one thin ring, is, so this is one moment of inertia of one ring, and we know the formula. If the ring has mass m and the radius are just mr squared, right? So the mass is very small, and the radius is some r square, and the moment of inertia, if it's small, so the corresponding moment of inertia is also very small, so it's tiny moment of inertia, di ring. Okay, then we say that the disk is just a sum of many rings. Okay, so many rings. The first ring is 0 radius, and then increasing, add up all the rings until the final one is radius r. So my moment of inertia of the disk is just the integral of all the rings. Okay, so my ring formula is now this. So I got dm and then r square, but I have my expression for dm over here, so let's put this in. Okay, so let's put this in and see what happens. So I have now my integral of, just put the whole thing in, so 2m over r square r dr, and then there's another r square at the back, right? So just be careful, rearrange everything so it makes sense. The constant can take it out, so I got 2m over r square, right? And then I'm integrating, there's r square and r, so it's r power 3 dr. Okay, so r power 3 dr, then just put in the limits, right? So my first ring is radius 0, my last ring is radius r. Then work out the integral. What I have here is 2m over r square. Integrate this, I got 1/4 r4 from 0 to r. So once I calculated everything, this is r to the power 4, right? So let me put it here. So r square 1 over 4, and then big R to the power 4. So cancelling this and cancelling this, I got half mr square. Okay. Yeah, here comes beautiful, right? So yeah, everything, like, it seems like everything just naturally falls into place together. And so regards to the earlier question, right? Yeah, student always asks, do I need to memorize the list of moment of inertia? This list. And this is also related to, like, if you ask me any tips to study physics, right? don't ask the question whether you're supposed to memorize it, because if you study enough times already, you will just naturally remember it, and that is a better way to remember something than sitting down and just say that, oh, this object is half mr squared, this object is mr squared. Memorizing doesn't give you understanding. Okay, that is the key to study things like physics and also math. In high school, maybe secondary school, primary school, because the things are more simple, so they train students to memorize everything and all the time. Okay, but if we want to start working in physical problems, solve actual problems, memorizing, there's no point, right? Like if it's a problem that you want to solve, you cannot think of the equation that you have memorized and then you plug in the formula and somehow you get the solution. Do you think physics was actually done this way? Very rare, right? So, but on the other hand, if you about the moments of inertia, if we deal with it enough times, right? Once you've done a few tutorial questions, because tutorial question especially always involve a disk or cylinder, then once you've done enough times, you just remember it's half mr squared. Yeah, so that is the thing about memorizing. Don't towards the end you will remember, but do not sit down and memorize it. You just work through this a few times until you get it. That is better than just memorizing. Any other question? Yes, correct, you get it. Yeah, learn and memorize with exercise and application. Do the calculation again and again. That will help, because if you do calculation again and again, right, it's like it's like cooking, right? The first time you do, it's very slow and you don't know which one to do first. You don't know to put things there. Same with math, right? You don't know you use this equation first, and then but if you do it enough times, then I can sort of like prepare this first and then I do this later, then I can plug this in. It will become more and more efficient. So you start to find ways to make your process faster, and that is the reason why we practice physics and math. Okay, so what time is it now? Okay, about halfway through. Horrifying. Why is it horrifying? So let's start to do the moment of inertia of a 3D object. So of a 3D object. So a 3D, we now talk about the cylinder. First time. Correct. Anything is very horrifying for the first time. It's true for anything, right? But for some reason, people are more scared of things related to physics and math. But I compare it to cooking because I find it the same thing. The first time you want to try something, wow, it's so confusing, very difficult. And then, but after a few times, you get used to it. So now we want to calculate the moment of inertia of a 3-dimensional object now. Okay, so a 3D cylinder, the radius of the cylinder is r, and then let's say the total mass is big M, and it is uniform. Okay, so how do we calculate this? Okay, so let's draw the cylinder. Yeah, I guess you can easily guess it already, because we have already found the moment of inertia of a circular disc, right? It's half mr squared, and a cylinder is just you stack up many discs. So you got this thing over here, right? So so let's put my coordinate system. So this is my y-axis, right? And then, oh, we need to know the height also, right? So let's say the height is h, so y is equals to 0, y is equals to h. Okay, and a cylinder is a stack of many discs. So if we consider one slice, they call it a cross section, right? So a cross section of this piece, the thickness is a very tiny cross section, tiny thickness, so it's dy, and the radius is the same as the whole disk, so it's just big R. And because it's a thin slice, so it's a small mass dm. Okay, so the moment of inertia of one disk. Yeah, so we're going to do this later. So, but first let's talk about the total mass first. The total mass, this is a uniform disk, so this is a 3D object, right? So 3D object is mass per volume, so it's mass per volume of the object. And then now I start to use the traditional formula for traditional symbol for density, which is rho, right? If this is uniform density, it means that rho is a constant. Okay, so rho is a constant, so the dV I bring over there. Okay, so just like what we did for dA, but now it's a dV. And in the multivariable calculus, right, you will learn that the volume element of a small piece is the 3 variable dy, dx, dz. So if you integrate, you will do a triple integration, that kind of situation, right? But we actually can avoid doing this, since we just treat this as one a cylinder as many disks. So we just need to look at the volume of one slice. Okay, so so the infinitesimal volume volume of one slice is dV is, what is this? What's the volume of this thing? Right, it's just the area times the tiny height, correct? So what's the area? So it's just pi r square times the tiny height. So I'm going to put this in as my dV. So my dm is rho, and then is pi r square dy. Okay, so now I can get my total mass. Total mass, right? So we are practicing calculus. Total mass is big M. So the big M is obtained by integrating over all the whole disk. So I can sum up to get the total mass. This is the integral of rho pi r square dy. So rearranging, just put the constant outside, pi r square rho, and then I'm just integrating dy. Okay, so you're just integrating y from 0 to h. So the bottom one is position 0, the top one is position h. Then what you end up with is just the pi r square rho and then times h. So finally I got my expression for rho. Again, this is what we expected. The rho is the total mass of the cylinder divided by pi r square times h. So this is the volume of the cylinder. So this is what we expect. So this is the total mass divided by the total volume. What is the capital I next to dy? You mean here, is it? Huh? Yeah, inertia, but I just want to find which part you're talking about. But yeah, it's just in a moment of inertia. The capital I here is just moment of inertia. The cylinder. Oh, it's not the. Oh, it's not I. It's the arrow. It's not I. Yeah, it's not I. Okay, so we got the rho now, right? And now since we got the rho, we can finally rewrite the proper expression for dm. dm is this dy, and the rho is m over pi r square h, and then this is pi r square dy. Okay, so actually they cancel each other, so the dm is just m over h dy, right? So we got this now, and now we can find the moment of inertia. So we're going to start by talking about, well, one disk, right? So the moment of inertia of one disk, of if the mass is m, then the formula for moment of inertia of the disk is, what was it, half, right? So half mr square. So m, and then the radius is r square. Okay, and so if the mass is small, so for infinitesimal mass dm, then the moment of inertia will be I disk for infinitesimal. Yeah, so for large m, the moment inertia is very high. For m tiny, moment inertia is also tiny. So it's 1 over 2 dm and then r square. Okay, so the MOI of the whole disk, the whole cylinder. Oh, I forgot, but we kind of assume, right, the axis is passing through the center. So the cylinder is rotating about the center. If the moment, so the moment inertia of the whole cylinder is the I, and then we can integrate over the whole thing. So we just plug in. So half dm r square, right? And then the dm expression is over here. So we're going to put it in here, right? So my I is just integral of half dm is m over h dy and then r square. Okay, so maybe you can start to see something beautiful might happen again. I got m r square over 2h integral dy. Now the same as before, like the bottommost disk is position 0, the uppermost disk is position r, height. Okay, so if I integrate, I just get mr square over 2h times h, and h cancel. So the moment inertia is independent of, it seems the pattern that emerged here, we keep on noticing, is that the moment of inertia is independent of the direction parallel to the axis. So that is the moment of inertia of a cylinder. So about memorizing, right, is most of the question is either talking about a cylinder or a disk, is always half mr square. So easy to remember, right? Yeah, you guys probably can already remember now from here on out. Okay, the sphere is 2 over 5. So the sphere is different, and most of the time you just need to remember the disk, the sphere, and rectangles and rods. That's all. Okay, and then the rest, I will teach you a way to calculate the moment of inertia of, if you know the one axis, you can shift it to a new axis and still calculate it. That's the parallel axis theorem. Yeah, Wei Zheng. The calculation, yeah, like 80% of the time is just talking about the dimensions of this thing. Normally the dy is irrelevant. Yeah, seems like it. So if the dimensions are, if it's parallel to the axis, then it seems like it's independent of the height. The final answer, right, is independent of the height. It only depends on the perpendicular distances. I suppose that should be the main reason why, because our moment of inertia formula mainly depends on perpendicular distances. Okay, so yeah, right, so the conclusion is, don't need to sit down and memorize. More importantly, just practice how to calculate moment of inertia. We have learned how to do it for one rod, right, a different axis, and then from the rod you can build, starting with one rod you can build a door. Okay, so that then you already know how to do the two things. And then what we just did here is, well, we have started on Monday by calculating the moment of inertia of one ring, right? So using the ring we can build a disk, then we can calculate that. And now that we know the disk, you can build the cylinder, and we know that as well, right? So we now know how to do the moment of inertia of at least 5 objects already. Okay, then you can, so in the lecture notes I included a list of other more common objects of moments of inertia. So we know how to do all, this one, and this one already. Maybe you can challenge yourself how to get this formula. Maybe if you want, I can show it to you on the Monday, right? And we have done this already. And then hollow cylinder. Hollow cylinder is just a stack of rings, so you get mr square, right? And then hollow cylinder with an inner and outer radius, got this formula. And for a sphere is this formula. Yeah, so we probably know half of the basic ones already. Okay, so that is the important thing. Yeah, practice calculus. Most of the time is just dimension. Yeah, I was saying, right, it's in, yeah, that's why it's so beautiful. Chiru was saying it's independent of the direction, but it is the formula. Okay, the reason why is because the symbol m for the disk, right, hang on, for the disk the moment of inertia is half mr square. The whole mass of the disk is m. Okay, for the cylinder the formula is the same formula, but the m refers to the mass of the whole thing, so if the total mass is the same, if you can find a cylinder with 10 kg and radius 1 meter, and another cylinder that is a disk, a thin disk, but it's also 10 kg, so it's more dense, and the radius is also 1 meter, they both have the same moment of inertia. Okay, why they are the same? Well, we have calculated what the reason why is the cancellation here. Okay, so they cancel and they left behind with mr squared. Any other question? Okay, 47, so we got some time left. Let's do some examples. Okay, so I think I will leave the parallel axis theorem to Monday. We got plenty of time, so we will talk about parallel axis theorem on Monday, but let's work out some examples. So example 5.1.1. so we spend so much time calculating moments of inertia, but how to actually solve problems. So let's say I have a situation like this. Okay, pull this up on the OBS. For a sphere, is more tricky. So yeah, okay, we'll do it on Monday because we'll probably need to do the tutorial soon. So we'll do it on Monday, and also the parallel axis theorem. Okay, a light non-stretching cable for a solid cylinder. The mass is given 50 kg. So yeah, just write it down since I'm reading it. The m is 50 kg, and then the diameter is 0.120 meter. That means the radius is 0.6 meters, right? Rotate about frictional axis. So it's being pulled by a force of 9 newtons over a distance of 2 meters. So displacement is 2 meters, and the cylinder turns, and the cable unwinds without slipping. So without slipping means something. I will go to that later. Cylinder is initially at rest. Then how do we find the linear speed after you pull it by 2 meters? So okay, let's see how to do this problem. What we have is a cylinder. So let's draw the cylinder like this. Okay, and then R, and then there's a cable that is wrapped around the cylinder, and then you pull it, right? So you pull it like a like something like yo-yo. Okay, so yo-yo, and you pull it by a force of 9 newtons. Okay, so you initially you start from rest, and then you pull it. It will extend by 2 meters. Okay, then it will start to rotate. So how do we find the if there's no friction, how do you stop from self-spinning? You mean it will spin? It will spin. So if there's no friction, oh, okay. So yes, there's no friction. So that means, right, if you let go of the force, if you let go of the string, it will continue to spin by itself. That is true. So we're not going to stop it from spinning. We will pull it until it spins. Okay. Okay. So how to solve this? Well, this is a cylinder. So a cylinder means the moment of inertia is half mr squared. Right? We have just calculated it. Then how do we solve this problem? Well, we shall be using the work energy theorem, because there is a force that is being acted upon over a certain displacement. So work is being done into the system. So let's talk about the work energy theorem. Okay, so the work energy theorem is to say that the work done is equals to the change in the kinetic energy of the system, right? So the work done is just force times displacement, so it's just Fs, so 9 times 2, and then this is the kinetic energy, and then this is the initial kinetic energy. Okay, then just work it out. So this term is 0 because it starts from rest, so this term is gone. Then we just need to calculate omega, so omega square is just 2Fs over I. Okay, then yeah, 2Fs over I. And what is I? So 2Fs, I is half mr square, which is to say that this is 4Fs over mr square. So my omega is just 2, the square root of F times S over mr square. Okay, so F is 9, S is 2, M is 50 kg, the radius is 0.6 meters. So if you calculate the value, you will be getting 20 radians per second. Okay, so that is the angular velocity of the rod rotating. Then find the linear speed v of the cable. So v is the linear speed of the cable. So v is the linear speed of the cable. So this is where the no slipping comes in, right? So no slipping means the cable doesn't slide over the surface of the cylinder, which is to say that no slipping means linear speed of the cable is just equal to the tangential speed at the edge of the cylinder. Okay. Yes. So try to think about this for a minute, because this is important. When we go to chapter 6, right, people start making mistakes everywhere all the time. Linear speed of the cable is the cable, right? Cable is going a linear direction. This part is a point on the cylinder, right? So a rolling cylinder, a point on the cylinder is this. Okay, so we are talking about two different things here. No slipping means the value of these two numbers have the same number. Okay, because in the next chapter we will consider what happens when these two values become not the same. Become not the same means like the cable is like sliding over the cylinder, so they do not move together. But no slipping means yes, they are the same. Okay, so if they are the same, then V is equals to R omega. Okay, which is just yeah, so radius times this. So if you put in the numbers, 1.20 meters per second. Okay, any question? No slip, no loss, yeah, of energy, right? No slip, no loss of energy. Correct. So, and friction, right, we have seen in chapter 3 is a non-conservative force. So non-conservative force means the energy, the mechanical energy is not conserved. That means energy is lost from the system. The reason it doesn't slip because there is friction. Actually, we are confusing a couple of things. So there's two places. Yes, the reason it doesn't slip is friction. The cable is having friction with the surface, but the axis, right? The joints, that the thing that the cylinder that rolls around, if you oil it, right? If it's smooth, then there's no friction. So there's two places that might have friction. Here we assume no friction, right? It's just spinning smoothly, but there's friction between the cable and the surface of the cylinder. Yeah. Yeah, and yeah, and kind of why we set the question like that, because seldom, not sometimes we might lah, but we seldom consider the friction between this, but sometimes we might, but most of the time no. I guess now is a good time to take a break, so let's take a 10 minutes break and we do one more example and then we do some tutorial question. Okay, so let's do a 10 minutes break. Stop recording. Stop recording. Start recording. And start recording. Here. Okay, so yeah, so one more example, which is over here. So let me pull up the notes. Okay, so this one is applying the conservation of energy. So this is where calculator cannot help you because they do not give you the numbers, right? So a light non-stretching cable is wrapped around a cylinder of mass m, of radius r. So the cylinder rotates with negligible friction, right? So what it means is that the axis here have no friction, so it can spin around smoothly around the axis, and without friction. About a horizontal axis, fine, yeah, we know this. A free end of the cable is tied to a block of mass m released from rest of height h above the floor. So yeah, so how do we find the angular speed and the speed of the falling block at the end of, just before it hits the ground? So this is a conservation of energy question, right? So let's draw this. Okay. 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 So my cylinder is like this, the radius r, and then the mass is big M. Okay, so there's no friction about the axis, so it can spin smoothly. So no energy loss, right? And then my box is initially here, and then later it will fall down here, right? So it will unroll and come down here. So from here to here, the change in height is h. So we will use the conservation of energy, right? So conservation of energy. So according to the conservation of energy, it says that initially it start from rest, and then it come here, it will come at a speed v. So the initial system initially has start from rest, so zero kinetic energy, right? Then after it comes here, it becomes kinetic energy. Initially here, I got the potential energy. This potential energy will get converted into kinetic energy. So the loss in potential energy is changed into kinetic energy. So you understand what I'm doing, right? So basically is the mgh, right? So the change in potential is just like this, and then after is here, what is the kinetic energy of the system? So this is where you have to be careful. There are two things here: this box of mass little m and this box of mass capital M. This will be moving, so it will have a linear kinetic energy half mv square. This box will be spinning, so it will have the rotational kinetic energy, so it's got half I omega square. And this is a cylinder, so cylinder is half mr square. So I can put this in, right? So I got this equation now. So half mv square is equal to half mv square plus half, and then this is half big mr square, and then omega square. Okay, so yeah, so we got this equation now, right? So let me write one more line just to tidy up. This is 1 over 4, so this is half mv square plus 1 over 4 mr square omega square. Okay, now so the question again say this is no slipping. Okay, so it's no slipping and the string is inextendable. What does that mean? Well, this whole thing is just trying to tell you that the linear speed of this box is the same as the tangential speed at the edges of the cylinder. Okay, linear speed of the box or translational speed is equal to the tangential speed at the edges of the cylinder. Okay, so V is equal to R omega. Right, R omega is how you find tangential speed. V is this V, the speed of this box. So I got two equations, so we'll just substitute 1 into 2. Okay, so we're going to substitute 2 into 1. Okay, so I got mgh is equals to half m, and then v squared, so it's r squared omega squared, and then I got 1 over 4 m r squared is already omega squared, so I can simplify this equation. So I can factorize, let's factorize r omega out, right? Then I got half m plus a quarter m. Okay, so this is small m gh. Okay, then you can solve this to find omega already, but I just want to make things look a bit nicer. So 4mgh is equals to 2m plus capital M, and this is r squared omega squared. So we wanted the angular velocity, right? So omega square is, put the rest over, so I got 4mgh over r squared 2m plus m, right? So therefore omega itself is just 2 over r and then the square root, right? So mgh and then 2m plus big M. Correct? Did I do it? Correct. Yeah, looks correct. Okay, so I got the angular velocity of the spinning cylinder. Then the speed is just r times omega, so it's just times r. So I just get back this mgh over this. Okay, so I got my two answers now. Okay. Any question? I'm recording, right? Test. Okay. Okay, good. Okay, any question? No, huh? So on Monday we'll do parallel axis theorem, sphere. Don't feel like doing, yeah, do sphere and then the rectangle probably. Okay, so then I will do some of the tutorial questions. Yeah, although I don't see, I already uploaded the question, right? Do you still want me to do it? I'll do the hard one, the one on the spherical surface. So that one might need a bit of explaining. Then the other question, all the answers are there, so it's pretty straightforward. Okay, so if there's no other things, let us go to the tutorial. Okay, let's start with the tutorial. Let's pick a question. We do question 9. Okay, so I'm gonna do 9, 10, and this one here. So this one is the one that needs some explanation, I think. But these two maybe is tricky if you're not familiar with the concept of power. Yeah, because actually the topic of power is not difficult, right? And for some reason, a lot of students get stuck with power related question, and I suspect it's because the power section is too short, so a lot of people skip it, and then when the time comes to do that part, they cannot do. Okay, so let's do question 9. Question 9 is over here. Where is it? Okay, so a plane can generate 75 kilowatts of power, and the mass of the plane is 700 kilograms, and it climbs at a rate of 2.5. And this question is not clear enough, but it is a constant, so that means the plane is climbing upwards at constant speed. So if it climbs up at constant speed, right, that will tell us information about the force acting on the thing. Constant speed means zero acceleration, so net force is zero. So if I have a plane, okay, right, so I have a plane, what is the net force acting on the plane? So the plane has a weight as always, mg, right, and the engine will generate the force to make sure the plane stays up, right, and the force, of course, the configuration and everything is very complicated, but we'll just call this the net vertical component, the lift force, okay, and we know that the plane is going at constant vertical speed, 2.5 meters per second. Therefore, what is the net force in the vertical direction? If I take upwards to be positive, F minus mg is equals to ma. This one will give it 0, right? In other words, my lift force is equals to mg. Okay, so that part is pretty straightforward. Now we want to calculate the power that is related to lifting the engine. So power used for lift. Okay. Tutorial 3, yeah. Tutorial 3. So we haven't finished all the questions on tutorial 3. And our quiz is until chapter 3. So yeah, so next week we will spend more time doing tutorials since we are a bit ahead of schedule. So next week we will do tutorial 4. The power used for lift is, well, the power is using the formula force times velocity. So force times velocity, right? And we have found the formula for the force is just mg, so it's mgv. So basically it's very simple, right? So 9.8, and then the velocity is 2.5 meters per second. So the answer that we get is 17.2 times 10 to the power 3, so it's 17.2 kilowatts. Okay, so this is power used for the lift, but you are given that the total power, P total, is 75 kilowatts. So the ratio is just the power used for lift divided by the total power. So it's just 17.2 over 75 and is 0.23. Okay, just like that. Pretty straightforward. Any question? Yeah, we are in tutorial 3. Then, so the next thing, right? Yeah, so someone pointed out and made me realize there's a typo on this question. So let me explain to you. So because the question is using the unit horsepower, and we shouldn't worry too much about it. We are using SI unit. So this question is from the textbook, and it talks about this. So we have an elevator of mass 60 kilograms, not including passengers. And the elevator is designed to go up at constant speed, a vertical distance of 20 meters in 16 seconds. So here we might as well get the speed. The speed is 20 meters, constant speed, right? So constant speed, I'll just take the total displacement over the total time, which will give me 1.25 meters per second. So this is the speed of the elevator. And the mass of the elevator without passengers is 600 kilograms. And it's driven by a motor that can provide up to 40 horsepower. So the power is given by 40 full screen, 40 horsepower, and according to the question given, 1 horsepower is what was it, 735.5 watts. Okay, and so 40 times this, so you can calculate this in terms of watts, right? So it's just 40 times 735.5, okay, watts. So I got the power, I got the mass, I got the velocity. So what are we supposed to calculate? We want to calculate this. What is the maximum number of passengers that can ride in the elevator? So this is a practical situation. Using the concept of power, we can calculate the maximum amount of passenger the elevator can support. So we assume the average passenger has 65 kilograms of mass. Okay, so what happens is the following. We have a lift. Okay, so we have many passengers. By the way, yeah, it reminds me, did anyone try the weighing machine inside the lift? Do you try it? Do you get a different weight, and can you calculate the acceleration of the lift? Okay, so this is the force, again used for the lifting, right? And then, so the passengers, right? I want to calculate the total number of passengers. So, but one person is about 65 kg. So 65 kg times n, and I don't know what is the total number of passengers. So it's 65n, and then the lift is this. So the weight of the total system is small m plus capital M times g. Okay, and the question says that elevator goes at constant speed. What time is it now? Okay, plenty of time. Okay, so elevator going at constant speed, that means the net constant speed, zero acceleration, so net force is zero. F lift, upward force, minus the downward force is equals to 0. Okay, so my F lift is equals to m plus big M times g. Okay, so this is how we got this situation. Okay, so now we want to calculate the power. So the power is just force times velocity. So the force of the lift times the velocity, which is just this times this. Right, and this is what I mean by memorizing lah, right? Because secondary school student, if you learn it in that style, right, they memorize this as mgv and then they apply the formula, but if the initial assumption change a bit, then the formula is wrong. So always, yeah, so my more tips for studying is start from the basic concept and make sure you can get the correct formula from the beginning, right? So you can understand the steps from beginning to end. But so now we got this, and then we just need to determine the m. So that's pretty straightforward. I want to solve for m, right? So from here I have P over GB is equals to small m plus big M. So therefore small m is equals to P over GB minus capital M. And m is 65 kg times the amount of passengers. So the numbers are all here already, right? And once we calculated everything, we get about 28 people. Okay. So any questions? Okay. So let's 22. How much time do I have? Let's do question 11. Let's do question 11 before the spherical surface, since we have the time. Okay. I think I uploaded the answer already, so everyone knows the answer and nothing straightforward. But before I gave the answer, right, I bet a lot of students was stuck trying to solve this. It's about this force. Okay. So I have used this question as a quiz before and as midterms, and usually a lot of people cannot get this right. Hang on. Yeah, so question 11. Correct. The power is also instantaneous. So at the instant, yes. So in both situations, so if the V changes over time, then the power changes over time. The power is the value at one instant. Yeah. Right. The power is the value at one instant. So if the V increases, so the power at that moment also will increase moment by moment. What else? Okay. So let us look at question 11. A particle of mass m starts from the origin, okay, and it has a non-zero initial velocity. So it has some, it doesn't start from rest. As the particle moves along the x-axis, it experiences a variable force. So F is equal to F sine constant times x, okay, and F and C are constants. So find the particle velocity when f first reaches a minimum. So before we continue, right, we need to figure out when does the force reaches the minimum. So when f first reaches minimum, maximum, yeah. Okay, so that means how do we reach maximum? It's a sine function. So to make this number the largest possible, sine must be equal to 1, right? It cannot go any higher. So to make that means it reaches maximum when sine cx equals to 1. So the first time this happens, starting from x equals to 0, is where cx is equals to pi half, am I right? Which is to say that x is equals to pi over 2c. Okay, so this is the point where it reaches the maximum. So then we want to calculate the work done, because that will tell me my velocity. So if I know the work done, I can use the work energy theorem to get my final kinetic energy. Once I know my final kinetic energy, I can find the speed. Okay, so work done from this position to this position is given by this formula. Okay, so I go from this position to this position. Okay, so this is where I've used the work energy theorem. So the work energy theorem is the change in kinetic energy. So the final kinetic energy is because it's moving at some speed v, and the initial kinetic energy is some initial speed v0 square, and the force is given by f sine cx. So f sine cx dx. Okay, so we just need to integrate this function. So it's basically just f over c cos, right? Cx. See, we are doing more calculus, so more integrations and differentiation, so we need to get used to it. Yeah, so just need to calculate the difference, right? So we plug this in, f over c cos c times pi over 2c, so it's just cos pi over 2, and then minus minus gets a plus, so f over c cos 0. So cos pi over 2 is 0, cos 0 is 1. Okay, and then the half mv square, I bring it over, so I got half mv square over here, and then half mv0 square, and I got a plus f over c. Okay, and then just rearrange, v square is equals to v0 square times 2 divide by m, so I got 2f over mc, and then we take the square root, which is the answer. So v0 plus 2f over mc, like this. Okay, any question? No? Okay, test. Okay, right. So let's now do the spherical surface question. Okay. So yeah, I keep thinking of random advice I can try to give people. Another advice probably is try to solve the question without looking at the answer first. That will be quite helpful, because it will make you think in your own way. Okay, if you refer to the answer, right, then you're just following what the answer is telling you, but if you don't look at the answer, it is a chance for you to think in your own way. And most of the time, if you think in your own way, you can get a solution. Maybe it's different method from the final answer, but that's fine. Because thinking in your own way and develop your own creative process is also important in solving problems. Okay. Not to say must lah, but as long as the answer is correct, right? And usually we don't care like what way you do it, as long as the answer is correct. So yeah, maybe like related to what you said last time, right? instead of integration, you can just find the area under the curve. That's fair, right? Nothing wrong with that. So that kind of situation. Okay, so I have this problem here. The skier start from a hemisphere. Okay, so this is a very standard question in Newtonian mechanics. So at some point we should learn how to solve this because it helps us understand a lot of concepts. So I have a skier start from rest on top, and then she will slide along the surface, right? But of course, if we play something similar like this before, right, we can imagine she will end up leaving the surface, so she will fly off at some point. But what is the position where she starts to fly off? This is what we want to calculate. So this is where again we combine circular motion with conservation of energy. So let's start over here. Okay, so the skier starts from position 1, and then over here is position 2. Okay, so I start from rest, and then when I'm at position 2, I'm having some speed v. So let's consider the energy of the system. So what is the conservation of energy? Okay, so if I start from rest, right, the kinetic energy when I'm at position 2 is equals to the change in potential energy, right? So high to low potential, so the potential energy convert into kinetic. So I got mg times the change in the height. So how to find the change in the height? Okay, so it's this way. So let's say the radius of this hemisphere is r, and then the angle is given to be theta, right? So this distance is r cos theta. Am I right? And then this distance is what? This distance is the change in height, because initially it's height here, and then I come down to this height. So this is my change in the height. It is actually the full radius minus the bottom part, so it's r minus r cos theta. Correct? Agree? Right? So this is actually, let me do this line. So mv square is equals to mg. I can factorize the r, and then 1 minus cos theta. Okay? So the m will cancel, and I have a formula for the speed later on. So it's 2gr, okay, and then 1 minus cos theta, right? So when theta is 0, the speed is 0, and then if the angle increases, the speed will increase. Okay, so this is just talking about energy, but we want to consider whether the skier leave the surface or not. So we need to look at the forces. Okay, so we draw the free body diagram at position 2. Okay, so at position 2, this is portion of a circle, right? So it's she is somewhere over here. Okay, let's look at the forces. There is, as always, the downward weight, right, mg, and then she is touching the surface, so there is a normal force, right? So if I take the radial direction, I can resolve my mg into this way, and this shall be, so theta, right? So this is also theta, right? So this is mg cos theta. Do you agree? Right? Mg cos theta. Okay. So the radial, the force in the radial direction is, well, the net force in the radial direction, right, is this minus mg cos theta. Wait, I should do it the other way around. Yeah, mg cos theta minus n, right? So the centripetal force, yeah, centripetal force. So that means it will give me the radial acceleration, which is to say that this is mv square over the r. R is the radius of this circular motion. Okay, so this is in circular motion, right? And I want to find when she leaves the surface. So when she leaves the surface, n becomes 0. Okay, so n becomes 0. Then n becomes 0. I got mg cos theta is equals to mv squared over r. Okay, so I can cancel the g here. So g cos theta or Rg cos theta is equals to V square. Right? So I got two equations now. I got the equation for V square, which I can substitute here. So I'll just substitute equations 1 into 2. Okay, then I got Rg cosine theta is equals to, after I put it in, I got 2gr 1 minus cos theta, right? So gr and gr will cancel. So I got cos theta is equals to 2 minus 2 cos theta. So I bring this term over to the other side. I got 3 cos theta equals to 2 cosine theta is 2/3. So you take the inverse cosine, you get 48.2 degrees. Okay, so at 42 degrees, she will leave the surface. Okay, so yeah, what time are we at now? Yeah, it's just the same thing. Okay, so we got a bit of time, so why not let us continue with the parallel axis theorem. Yeah, so let's talk about parallel axis theorem. Can we just say cos 2/3? Technically, if the question is asking for angle, so if the question wants angle, we must give the angle. So we can say, yeah, we can say this. Yeah, so you can put it like this. That's also fine. Okay, any other question? Okay, so yeah, we have plenty of time, and yeah, it's a bit strange how come we seem to be going faster and faster as the lesson goes on. I suppose yeah, I don't know why. I would have thought that when the topics is harder, then we will go slower. Maybe not hard enough. Yeah, should come up with more difficult topics. Am I recording? Yes, test. Okay. So we will talk about the parallel axis theorem. And parallel axis theorem is another interesting concept if you think about it, because it, for one thing, is very useful. It's a good pace, don't too hard. Okay, fine. Yeah. Yeah, fine. You have a few more years to go higher and higher level courses where things get more and more difficult. That is definitely true, right? So we will do like yeah, like second year mechanics, second year thermodynamics, second year electromagnetism. All this will get harder. But I would say, ironically, it becomes easier. Yeah. So yeah, so let us talk about this thing. Okay. So let's say I have an object, right? The center of mass is here. Will we learn aerodynamics? No. If I remember correctly, we don't have a specific course for aerodynamics. Your first year thermophysics already feel like third year, is it? Or yeah, I think it has to be because thermophysics is actually a very, very big topic, very, very complicated field. So so which is the easiest course you guys are taking so far? This one, thermophysics, or calculus, or linear algebra? Python. Fluid dynamics. Do we have? I think we have a fluid dynamics course. It might third year, I think. Yeah, I think it's on third year. Python, yeah, Python easiest. I can see how. Yeah, I can see why. So let's say I have an object, right? The moment of inertia. So let's say I have the center of mass, and also the axis of rotation is passing through the center of mass. And let's say I know the moment of inertia when this is my axis. That time when we are talking about rods, right? I have shown you that if I change to a new axis, the moment of inertia change. So this theorem will give you an easy formula. So let's say this is my new axis. Okay, but the condition is these two axes must be parallel. Okay, and then if I shift the distance between the old and the new axis is d, I can, according to the parallel axis theorem, the new moment of inertia, you don't need to do the integration again, right? Don't need to repeat everything again. If you already know this, then save your effort. You just plus m times d square, the distance square. So this is the parallel axis theorem. Okay, so that is very straightforward. So let us prove the parallel axis theorem. So what time are we now? Mechanics is the easy one. Okay, that's good. Okay. So let's try to prove. But in the lecture notes, the proof is given for a general two-dimensional object. But since it's a bit more complicated, right? So let's make it easy. Let us prove this case in the one-dimensional. So proof in the 1D case. Okay, so so how to prove this in the one-dimensional case? So the first thing that we want to do, right, is to fix the coordinate system. Not exam yet. Yeah, we shall see. Okay, so so let's prove this in the one-dimensional case. To start with, right, the axis is important. So let us fix the coordinate system such that the center of mass is on the origin. Okay, so that means, right, if I talk about a rod, okay, so we should be quite familiar with the rod already. We have calculated the moment of inertia of the rods for different axes, right? This is my x-axis, and let's say this is my center of mass. So if this is my previous axis, the position of the center of mass is 0. This is the origin. Okay, so I purposely put the origin on the center of mass. If it's not at the origin, I can move the x-axis so that the 0 goes to the center of mass, right? And remember last time in the momentum chapter, we have calculated the center of mass is given by x integrate dm, right? And if this is at the origin, so this should be equals to 0. Okay. Okay, so this is what we have now, right? So this is my original axis or O axis. Okay, so my O axis it passes through the center of mass. So the moment of inertia of the center of mass is something that we can easily calculate. It's just the integral of r squared dm, right? So r squared dm. But remember how we calculate? We first consider a small piece, right? Small piece dm, and then the length is very small, is the x, and we need the r squared. So if I put the origin as my center of mass, so the r squared is just my x coordinate from the axis. So ICM is just equals to x squared dm, right? So this is the distance from center of mass, and the distance from center of mass is the same as distance from the axis, the O axis. Okay, so this is the original center of mass. So what I want to do is I'm going to shift my axis to a new position. Okay, so let me draw again a rod. Okay, so my center of mass is here, so center of mass means x equals to 0. Okay, but my axis is no longer here, so let's say I shift it to a new position. Okay, so I shift it to somewhere here. Okay, so this is my new axis. So the previous axis to the new axis, the distance is d. Okay, then how do we find the moment of inertia? So the moment of inertia is, well, we can still apply the formula, the integral of r square dm. So let's check, look at 1 dm. So the dm, let's say I take one piece over here, the infinitesimal mass is dm, the infinitesimal length is dx, right? What is this position? Okay, so the position is some position x, okay, but I want to find r squared dm. So r squared dm, right, this is where you have to be careful. Right now, I cannot put x, right? X is the x coordinate, it's just this distance over here. This is my x coordinate. Therefore, this is my x coordinate. So the r, what is r? R is x minus d. Agree? Follow so far? Okay, so r is x minus d, right? Then, so the distance of dm, like one piece from new axis, is x minus d, which is to say that my new moment of inertia is x minus d square dm. So do you follow so far? Right? Is it a good story? Do you follow the story so far? Okay. So if you agree with this, right, then we are almost done, because all we need to do is just to expand the square and then just simplify everything and we'll get the theorem. Okay, so let's expand the square. So the new moment of inertia is squaring this, so x squared minus 2xd plus d squared and then dm. So it becomes 3 terms, so we integrate term by term. So my new moment of inertia is integral of x squared dm minus the constant. So 2 is a constant, d is a constant, I'm just integrating x dm, and then plus d squared is a constant, so I'm just integrating dm. Okay, then we notice something here. The integral over dm is the total mass. So this just gives me m. So we got our md square over here. Then what is this? So the integral of x dm, right? The integral of x dm is just the center of mass times m. So this is xcm times m. But we were saying that my origin is the center of mass, so this number is 0. Right? So this term is 0. And then this one, what was this? This one was what we calculated. This is the original moment of inertia. So this is ICM. Right? Which is to say that my new moment of inertia is ICM, and then this is md squared. So we have proven the theorem, the parallel axis theorem. Okay, any question? Haven't examined yet. Don't make conclusions early. Yeah, maybe you'll change your mind when the exam comes, right? So yeah, but maybe it will make you think it's even more easier. So who knows, right? Okay, but how about your other course? Will you have your exam soon? Should be coming soon, right? Okay. Okay, so next week, yeah, so thermal, yeah, thermal is next week, yes, definitely. Integral of xdm, what is it? I mean, I just said, right, xdm, what is xdm? Xdm is this, okay, so just write one more line. If I bring the m over, is integral xdm. So you just substitute this in. XDM is equals to this. Okay, any question? Yeah, so now it's exam season. Then, so yeah, everyone is busy studying now. Next week, live in fire. Yes. Will it trouble me if you put the quiz on tablet? No, it's fine. Yeah. So you can put it on the PDF tablet. Yeah. So just remember to save as PDF lah. No problem. The new axis drawing here. Yeah, the new axis. Yeah, this part I messed up the drawing, very ugly, but the original axis was passing through CM, and then the new axis is here. Okay, any other question? Okay, so yeah, I guess we're done. So we finished. We we don't have time. Yeah, we're kind of done, but as you said, right, you want to do the sphere and a few more moment of inertia examples, and well, let us finish this one last thing. So let us check the theorem for the case of the rod. Okay, so yeah, I decided to do one last thing before we go. Okay, so remember, right, for uniform rod, axis through the center, the center, which is if it's the uniform rod, is the center of mass, right? We have done this calculation. Okay, so I say don't memorize, but do you at some point you will be familiar enough to calculate and get used to it, and eventually you will remember naturally that the moment of inertia is 1/12 ml square, right? So this is what we did on Monday, I think. Yes. So now if I shift this axis to a new position, right? So this is my old axis and this is my new axis. So my shifting is towards this direction by the distance d. So what is the distance d? Is just half the length of the rod. So it's L/2. So what is my new moment of inertia? So this is my cm. So this is my new moment of inertia according to the parallel axis theorem. The formula is taking ICM plus md square. Am I right? So the ICM is 1/12 ml square, and then I shift it by this distance. So this is m times L/2 square. So I got 1/12 ml square, and then half square is quarter ml square. So as you can see, this plus this is 1/12 plus times 3, right? So 3/12 ml square. Then we see 3 plus 1 is 4/12 ml square. So 4/12 is 1/3 ml square, which was what we got last time by calculating from the beginning, right? So we can see that, yeah, this theorem is true, right? So this is the fun part of proving theorem, right? It's you from some indirect way, you got some formula, and then you use the formula, it always works, right? So that's a theorem for you. Okay, so yeah, so it's quite late already, so if there's no other question, that should be all for today. So let me stop the recording.